So let's talk about recursion, at least the basics of recursion. So far, we've seen that in any methods, we could call different methods, such as you could see here, I'm calling print ln, and inside print ln, I'm calling a different method print ln. And to be honest, we could call anything from anywhere unless we said otherwise. Don't create rules for yourself. Now, recursion is the possibility of calling yourself. So a method that calls itself as many times as required. And this could make our code much cleaner sometimes, or sometimes much worse. There's even more to it than that. So for an example, we're going to start with this one. We have a, oops, let's put that as n here. We have a number that we got from the user, 10. It could be any number. And what we want to do is add every number from 0 up to that value, so up to 10. So it will go for every number, add it to my total, and then we're going to print that total. So if we have 10 as our initial value, we get 55. And just to confirm that that's true, we could see that 1, 2, that's 3. Well, let's just do it quickly, not to waste too much time. All right. So 1, 2 is 3. This is 6. 6 plus 4, this is 10. 10 plus 5, 15. 11 with the 16. Sorry, let's put 11. So 11 and 10, 21. 7 and 8, 15. And 15 and 9, oh, sorry. That would be 24. 24 plus 21, 45. 45 plus the final 10 over here, we got our 55, right? You could do that calculations yourself. This is just to show you that it works. Now, this is great. We did it in a for loop. And to be honest, if we can, I would always suggest a loop over a recursion. But as beginner, forget that for now. Let's try doing everything with recursion as much as possible. So if we wanted to make the same loop, the same functionality, I want to add everything up to that value. We're going to create ourselves a method, signature, public static. Does it return something or not? We could return something, or we could just print it to the screen. Doesn't matter. Sum. And what we want to do is we want to know our total number. So what number to reach? So let's say int reach number, or let's say max number, if that sounds better. And we're going to do some other examples too, just to see what works. Maybe something a bit more interesting than just summing. So when summing starts, we're always going to add a beginning, and we want to kind of have in a recursion an end. So if you look in our loop, we have our beginning, and over here we have our end, right? When the condition is false, we stop our loop and we go away. Now for recursive methods, it's kind of similar, but you have to end them by doing the return keyword. So let's see how we would do. So every time we come in, we want to sum that number. So whatever the total value is, and we want to call ourselves and add the next number. So what I want to do, first we're going to do an error. What I want to do is I want to call myself sum, and I want to go to the next number. So max number, we're going to do -1. So here, if the max number was 10, when I'm calling myself again, I'm calling it with 9. Right? And that number, we want to, let's say we're going to make it a bit longer. Int, let's say that's our total. It's going to be the current value, max number, plus sum max number -1. And at the end of all of this, we need to return our total. We need to give it back. So what's going on here before we run it? Well, this is the current number. So let's say if I call my method at, let's say over here, rather I'm going to keep this loop here for now, okay? But let's say if I do sum and I wanted that n. So the first initial time I'm calling it, the value coming in is 10. So sum 10. And when we come inside here, we got 10 over here. Our first line 17 says total equals 10 plus, now we're calling sum, but we need to do this operation. So 10 minus 1, we're calling it with 9. So we call, so from this one, we call sum, and we pass it 9. So we're back to we're back to here, but this time we have our value as 9, and we're doing total equals 9 plus sum 9 minus 1. So sum again 8, and it's gonna keep on going if you notice. So we hit our first problem. Can you see what the first problem is? The first problem is we never said when it's going to end. We said the initial start. Here at line 13, that's our initial start. But there is really no end. We're just calling ourselves nonstop recursively. So when this happens, we get a method overflow or a function overflow, whichever one you want to call it. What's going on is, you could see here, at some point, we don't have any more space. All right, a stack overflow, the initial thing. This is because we never reached an end, but every, let's say, program, application, etc., we talked about the stack and, no, I'm having a brain fart right now. But we've talked about how there is a specific amount of memory corresponding to each application or to each method, functionality, etc. And in this case, we've passed the amount allowed or allocated to our application. So we get this type of error called a stack overflow. So here, we need to have an ending. When should I end? Ending in the case of recursive methods, not always, but normally you would like to have that at the beginning of the body of that method. So if our max number is equal to 0, well, there's no more anything to add. We could say return 0, right? So this means that when our number reaches 0, it will stop. It will not go in negative as we've been doing it, right? Here, if it was 0, 0 minus 1 would be minus 1. It would still call it and it would continue. But in the case that this value starts at 0, well, it will stop right away. We could have even said if it's less than 0 or equal to return 0. We don't want negative numbers, as an example. Okay, you could have also done negative number, but we're summing up to this number. We don't want to go negative. We could have changed our thing for other optionalities, such as beginning number, end number, etc. Doesn't really matter. Now, if we run it again, let's see what happens. Hey, we got our 55. Well, we got no errors. We didn't get our 55 because this is showing our loop. So let's go do a system.out and put it inside there. So you could see that we have our total from our loop, and we got our total from our recursive loop, let's say, our recursive sum. And both cases, they equal 55. Now, which one's better is up to you. So again, we could call our method many times itself. Just remember that we want to kind of have our ending at the beginning or somewhere near there. And this is the basic. So there's going to be other things we could learn about recursive methods, but something important is we have a maximum that we could reach. Otherwise, we get something called a stack overflow. Now, this stack overflow happened here because we did an infinite loop, but it could also happen when our n is just too big. So what if we add a couple zeros? Let's say 1000. Let's see. Well, let's try first with 100. These two values should both show the same value. 50, 50, perfect. Let's add another 0. Let's run it again. We're pretty good. 500,000. Let's add another 0. We're going to see what's our limit to our Stack Overflow. It's pretty good. Let's add another 0. We reached it when we tried to have 100,000 numbers. So let's go up, 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 up. So you could see over here, the first number here, this is our loop. Our loop got the value it needed, but our method recursion cannot reach that value because of Stack Overflow, because there is a maximum allocated to our stack, a maximum amount of space. And we'll talk about that in future videos, more about memory. But for now, we need to understand there is a limitation to our recursive method. Mind you, a recursive method makes a lot of code cleaner. It might be ideal to use it inside of an interview, but you need to maybe let them know, or maybe make sure they understand that you know the limitations. Now, let's, if you want, you could stop the video here and move on to the next one. I'm going to do a few different examples to see where recursive, it will show how it's a bit cleaner in the eyes, and how we would do it inside, let's say, a for loop. All right. So let's start talking with something called the Fibonacci sequence. Fibonacci was this guy who was trying to count the amount of rabbit birth cycle. So how fast are they going to reproduce? And it was completely bogus, but he created an interesting sequence where we add the last two to give the next value. So there's two things here you're going to see. I should have maybe named them a bit better. These are the values. These are the positions. So at the beginning, there's no rabbits. There we go. I'm forgetting names. So at the beginning, there's no rabbit, but there is one rabbit. And let's say them together. Actually, just to let you know, sometimes in Fibonacci sequence, you'll forget this position 0, and you'll start off with these two. Position 1 and position 2, which basically both have one rabbit. Both of these rabbits together will give you the 2. That's position 3. Both of these rabbits will give you the next one, which is this one. Both of these together will give you the next one. 3 and 5 together, right, will give you the 8. 5 and 8 together will give you the 13, and so forth, so on. You can see that the last two positions give you the next position. So to get position, let's say 8, you need to add position 6 and position 7. So these ones. What are those values? Well, it's 8 and 13. 8, 13 together gives you 21. Okay? So, knowing this, give me 1 second. I'm going to just add here values and position. Knowing this, and I was trying to line them up. Knowing this, let's go ahead and build a loop to be able to do it. So over here, this is the user's position. So I selected I want 10. I want you to give me what is at 10. So we could see here is 55, right? Just to make sure it works. And if I say 11, well, then it should give me 89. Yeah, good. So it's working. Our code is tested enough for it to function. And it's simplified enough that we could all understand. So our current position, I will start at 1. There's no point of starting at 0. There's no meaning to it. I should have probably not even mentioned it, but whatever. So what I've done is I hold on to the value of the previous, and I hold on to the current value. I started my loop at the first position, and I tried reaching the position asked for. So I'm going to go until that position. This loop is just repetition. You'll notice none of the variables inside there is actually utilized in my body. Inside my body, the only thing I'm doing is I'm taking the current and holding it into a temporary variable, making the new current, with the previous value. So remember, the new value is the two last values. So all I'm doing is adding the second previous into my current value. And in the end, I put that temporary current back to the previous. So now my new previous is one ahead, right? Maybe I should, my naming wasn't so great. I'm a bit tired. So my naming is, see, this is why clean code is important. But let's go through it. So as an example, let's say my current position is at 5. So this is my current position. Okay, we don't really care about any of these variables. They're not utilized inside the body. What is in the body currently? We create a temporary variable. Let's say this is our temporary variable, temp. And we add the current value in there. Well, the current value is not where our position is, it's the previous time. So again, my naming, I'm really sorry, I was tired. So the current value is this one, and the previous value is this one. So what we're doing is putting the 3 in here, inside our temp. Then on line 15, we're saying the current plus equal the previous. So add the previous, this 2, onto the 3, which will give you 5. So the current is now 5. Does that make sense? You just rewind, try it again. And then the previous, so this 2 right now needs to go to 3, but we lost track of this value. Well, here we have it inside temp. So what we're doing is making that variable on line 16 equal the temp value that we have, whatever it is. And we keep on doing that until we reach the position demanded. Okay? Nothing too complicated. And it gets more interesting when we go on higher values. So position, you'll notice that at 11 is 89, but let's say if we go like a few positions higher, you'll notice the value is exponentially getting higher. It's 900. Maybe let's say 20. We're at 6,000, and it increments really huge amounts. Okay, so this is how we did it inside of a loop. Can you do it inside of a method now using recursion? Go ahead and pause it, do it your own. I'm going to just get started, and we're going to go step by step together, understanding how we could reach that. Now, again, there's many ways that you could do any code. So if you did it differently, it's perfectly fine. So the first thing is we're going to create a method, signature. I'm going to keep it void for now. And we're going to say Fibonacci. And we need to have a position that we want to reach. So let's say this is the max position. I don't know. Okay. Now, as previously stated, we need to specify when are we ending this. So we could do it two ways. We could start from position 1 and reach the top. But can we start from the max position and reach the bottom? So let's say if I started at position 11 and I wanted to reach position 1. Well, actually, if I start at position 11, there's no need to go backwards, right? So that makes no sense. And secondly, I wouldn't be able to know 89 because I'm reliant on the previous positions. So this is not working. So we have to start always at position 1 and go upwards. Obviously, if you're seasoned, you'll notice there's ways that we could retain memory, something called memoization, not memorization. Anyway, for this, we're just going to go the easy step. So we're going to start at the beginning, and we're going to try and reach the max position, or the position that we're looking for. Okay. So how should we do this? Right. So we're going to start at position, and we need to call ourselves with the next position. How would we end this? We could come back to it in a second. So if I were to add these two numbers, let's say I give it the max position of, well, let's say if I give the position 1 or 2, in those cases, if the max, let's say position, we could just say position. If the position is 1 or position is 2, well, right away, we could see that the value in both of these cases is 1. So we're just going to return 1. And to be honest, this seems to be our edge case, our end cases. When should our recursion stop? We're going to come back to it. We're building it in a different, strange way, but we're going to come back to it. Now, if it was in these two positions, if it was at position 3, we need to be able to add the two previous ones for it to function. Actually, here, let me erase this. It's gonna make more sense if I erase this. Let's do it in a completely different way. We're gonna take our little drawing board so you could kind of see how we would develop this. Let's say I wanted to have position 8. Okay, this is my goal. For position 8, what I need to do? Well, I need to add position 6, and I need to add position 7. Okay, that's pretty straightforward. But I don't know what position 6 is or 7. For position 6, I would need to know position 4 and position 5. For position 7, I need to know 5 and 6. For 4, I need to know 2 and 3. For 2, I need to know, well, in this case, 2 is already known, right? Let's say at the beginning, they're always 1, 1. There's no point of going to 0. Okay? So let's say 2 and 1, they're known. It's going to make my life easier. They're always 1. So this is pretty straightforward. This is value 1. For 3, I need to know 1 and 2. For 5, I need to know 3 and 4. This 3 is already specified here, but for this, I need 2 and 3. You know, it comes back, right? Many times we're repeating the same time. So again, recursion is not the most efficient way. It could be if you tweak it a little bit, but it has its ups. So coming with this value, knowing this value is the position I'm checking, we're going to have to add the two previous positions. So we need to add Fibonacci position -1 plus Fibonacci position -2, right? Notice here 8, position -1 would be 7, position -2 would be 6. Cool. The only problem is we're going to have an infinite return. So let's switch this to int. So right now, if I run this, let's go over here. And we're going to call Fibonacci, and we're going to give the same position, position 20. This should return me both the same value. But you'll notice we're going to get a stack overflow. What happened? Well, scroll this up. What happened was we never put our end cases. Where's our end cases? As you could see, this tree that we've created on the right side. Well, it's when we reach 1 or 2. Why? Because those are the two values we know it's always 1. It's never going to change. The rest we don't really need to memorize. So if position equals 1 or position equals 2, then we should return a 1. Right? Obviously, if the guy puts any values under this, this is going to break. We're just doing it assuming that any values is entering is going to be bigger or equal to 1. Okay, so let's try this again. And if you notice, we got both the same number. Hey, that's great. Is this efficient or not? Well, not really, because you'll notice that that 3, as an example, comes back many times. That 4 came back 2, 3 times. That 5 is going to come back 3, 4 times. That 6, same thing. Right? It's not efficient because we're not remembering what the value was for that, let's say that 4 over here. That 4 is already done once, and we should have somehow remembered that 4 is always going to give us 3. Or that, let's say that 5, we see it's always going to give us 5. Or that 6 is going to give us 8. Right? What if this number that we're looking for in the Fibonacci sequence is not a simple number? What if, well, this is a great example. What if it was 20? Well, to calculate 20, I need 18 and I need 19. To calculate 18, I need 16 and I need 17. To calculate 19, look here. I need 17 and I need 18. So this 18 that we're doing on the left side already required on the next side. That 17 is required twice. And we could see it many times as we bring this lower or higher position that we're looking for. A lot of things is going to be repeated. So in this case, the bigger the value comes for a recursion, the slower our application will get. So what if our Fibonacci here was 50? Actually, maybe not too much. Let's say 30. We're going to go small amounts because it's going to break at some point. So with 30, we're doing pretty good. What if we go 50? Maybe. And you could see here, well, we got 2 problems. One, we got a minus, and we've talked about this. We got an integer overflow. And our application, as you could see over here, has not finished. So the application is still running, trying to finish our Fibonacci with position 50. Let's see. I'm going to pause the video while this is running. Hopefully it will finish by any time. All right, so it did finish. It took a long time to finish. Well, not that long, but like let's say a minute. And for a computer, a minute is a long time. And you could see over here that we got some errors, or it went negative when it shouldn't. And this is just because our integer cannot contain the value that we need, right? And that's our fault because we made them into integers for a position in Fibonacci, which goes at 50, which goes in the high numbers. So we could easily fix that by doing long most of these places. So long, 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 and let's say long over here. Cool. And if we run it, you'll notice again, the first one, which is a loop, comes pretty much instantly, right? Even though it's not efficient, and so for some we would talk about in the future videos. But for now, you'll notice this loop finishes instantly, while the Fibonacci, which is creating or recalling or recurring methods, it's taking massive amount of time. And we're talking about computer time, where a second is a whole world eclipsing on itself, basically. It's not the best wording, but yeah, let's get to it. So thanks for joining, guys. I'll see you guys in the next video. I'm just gonna waste my time and your time to see when this would finish, and hopefully with the YouTube timer going through, you'll see that it's finished at some time. Oh, there we go. All right, guys, I'll see you later.